Hey, it's Kyle back again, and before I start talking about part 2B, I have a quick comment about part 2A. Um, I was ending my Newton and secant method when the difference of the new guesses was past the tolerance. Um, that works, but it could also just say when my new f function value is less than the tolerance, because that's the actual zero we're looking for when the function is equal to zero. So I think I just like that one a little bit more than the way I was going about it. So both should run the same, shouldn't cause any issues. But just wanted to make a quick note of that. Alright, but now let's get into part 2B of the homework, in which we're going to be explaining and implementing Newton's method for finding the root of a vector function. So it's a very similar kind of style. We still provide one initial guess, and it's just a different way of calculating our new guess. And this way we can use Newton's method to solve a system of k equations by finding the zeros of k simultaneously. So the function to find our new guess here is our new guess is equal to our old guess minus the inverse of the Jacobian at our initial guess times the function value at our initial guess. So we're going to get into that right now. So it's going to be very similar, so we'll define another function. We'll call this one capital NEW. It's going to take in a function f, and it's going to take in an initial guess, and then it's going to do the same thing with the iterations and the tolerance. Alright, there we go. Alright, so now we got a for loop for I in range of iterations, and we're basically doing the same thing. So this time we'll call it f of 0, and it's going to be equal to our function f at x of 0 that I will define in a little bit. And then we got the Jacobian of our function, so we'll call that f jack. That is equal to jax, which I imported already, dot Jacobian of f. And then we can say f jack. Yeah, I guess we can probably say this now. F jax 0 is equal to. We'll wait on this one because we're going to be taking the inverse of it, so. Do that actually in the calculation. So yeah, now looks like we have everything we need to do our calculation for our next guess. So we'll come down here, we'll say x1 is equal to x0 minus the Jacobian. So we want the inverse of our Jacobian, so JMP, which I did not import, I don't think. Stop. NumP. NumP. Oh my gosh. Jax.NumP as JMP. There we go. Alright. So that'll help. So jmp.linalg dot inverse of f jack at x of 0, our initial guess. And then we want to do matrix multiplication with our f of 0. So use the at symbol times f at x of 0. And then we're good there. And then yeah, we'll do the same thing. So on a break, if we are meeting our tolerance, so this time we can't compare an array to our tolerance, so we're going to need to do the normalized version. So round.norm of our value f. Actually, sorry. Over f1 value, which f1 is going to be equal to f at x of 1. And we want to see if that is less than tolerance. If so, we break from the loop and we have success. If not, we set our x of 0 equal to the new x we calculated. And yeah, so let's run this, make sure I have no issues. Looks good. I don't think I ever returned. Okay, that is an important part. We're going to return our root. There we go. Alright, so now we want to make our function that we're going to be feeding. So we'll define so instead of making a two-dimensional function, I'm going to use this example. They already defined it for me, so I don't have to type define function. So I'm going to put that here, define function of x, and let me bring this back up here. And we want this to be an array, so we'll just make a jnp.array and close that bracket. Alright, return, run that. And now we should be good to call on our new function. Let's take a look. So call on Newton, and I feed it function that we just made. Our initial guess, actually, I'll do that separately. X0 is equal to jnp.array. 0, 0, we need it to be an array as well. And then we'll feed it our function and then x0. Function object is not scriptable. Function object is not. Oh! This could be why. Let's see. Alright, so that was that issue. And now Jax always needs floats, not integers. And there we go. So calculated the roots of our function. And like I did earlier, I like having this root variable just to make sure it actually did calculate the roots of our function. So let's check it again. And it did not converge. Alright, so what if we add more iterations? I probably should have went to 100 before 1,000. Let's give it a minute here. not converge, but it stayed at the same amount. Well, hold on, how many iterations did it run through? Did it run through 100? $99. Alright, so I was taking a look, and these are definitely the roots of this function. 0.8411, 0.84116, and 0.15883, 0.15883. So I think it might be a little weird trying to break from the loop by comparing this vector, or this like array, to just a normal tolerance value. That's just essentially 0. So I don't know if it's not really breaking from the function, but it does calculate the roots, and it is successful. So those are indeed the roots of the function.